Thank you very much for having me here. This is my first meeting as the new director of the Vatican Observatory. And I would like to point out that our budget is very similar to NASA's budget. We are 0.5% of the budget of the Vatican City-State. When I first arrived at the Vatican Observatory more than 20 years ago, as an expert in meteorites, I was delighted to discover that it has a very large collection of meteorites and of a collection more than 1,000 pieces of every different type. And my interest was to do measurements of their physical properties, magnetic susceptibility, thermal properties, and especially density and porosity. Back in the 90s, back in the 90s, we developed a number of in-house sort of homemade instruments to make these measurements. In the last 20 years, that's developed to much more modern commercial pycnometers, laser scanning. I've also been able to add to our staff Brother Bob Mackey, who's like me, an MIT graduate. And it's wonderful to have collaboration. Science is a collaborative activity, which is one thing that makes it different from philosophy. Among the collaborators that we've had come by include this local chemist who even brought his own white lab coat, very handy. The results of our meteorite measurements were that most meteorites have a density of about 3 to 3.5 times the density of water, but there is one type which are rich in water and carbon and very porous that have a density of around 2 times the density. Now, the reason that we're interested in meteorites is, of course, there's a connection between them and the asteroids. For a number of reasons, we know that meteorites come from asteroids. When they go through the Earth's atmosphere, they can be photographed. You can trace their orbits back. In every case, the orbit goes back to the asteroid belt. You can observe their spectra, and while it's not as distinctive as the spectra of pure gases, nonetheless, you can match the spectra of asteroids with those of meteorites. The Japanese, a few years ago, actually sent the Hayabusa mission to an asteroid called Itokawa, and brought back grains you can see in the tiny bits of grain in the metal canister there, which are chemically identical to the grains from a particular kind of asteroid. And there are right now a number of asteroid sample return missions in the works. OSIRIS-REx is already launched and en route to asteroid Bennu. Hayabusa 2 is in the works, and the Europeans are likewise looking at such possibilities. Just as meteorites can be divided into various types, but generally are either stony types or else dark carbonaceous types, the vast majority of asteroids come in 2 types, and it's very easy to make the connection between ordinary chondrites and the S-class asteroids, carbonaceous chondrites and the C-type asteroids. When you measure the density of asteroids, and only in the last 20 years we've been able to do that, we likewise see that they have the same sort of split in density that we saw in the meteorites. One difference is that when you compare the two, you realize the meteorites are significantly more dense than the asteroids that they come from. And the reason for this generally can be explained in terms of what we call macroporosity. The asteroids are generally not solid lumps of rock unless they're very large, and the ones above the purple line are now considered dwarf planets because they're able to pull themselves and pull out their macroporosity. But otherwise, you can see near-Earth asteroids are 40% empty space. Comets as much as 80% empty space. Dark asteroids 40 to 50%. Stony asteroids fractured to maybe 20%. In all cases, it looks very much as though these asteroids are not solid rocks, but bodies which have been shattered and reaccreted. And that also means, of course, that the surfaces we see are comparable to what's inside because everything's been mixed up. The nice thing about our work in measuring the meteorite potential density and the asteroid density is we can not merely wave our hands and say that they're porous, but we can put a quantitative value on their porosity. That's very useful if you're worried about an asteroid coming and hitting the Earth and you want to know how to deflect it. You have a much better idea of physically how it's put together. And even a small body like the lump of metal that hit Meteor Crater about 50,000 years ago set up winds that would have knocked down buildings in a radius of 40 to 50 kilometers. Larger asteroids, of course, have significantly larger effects. However, what I want to concentrate on today is another aspect of knowing how an asteroid is put together. If we know the size of an asteroid, we know how much of it is empty space, we know the rest of it is like the meteorites in our lab, you can calculate the value of the mineral wealth seen in an asteroid. This is a value for a 1 kilometer diameter stony asteroid, assuming it's got the composition of an ordinary meteorite. This is a calculation I've done this week on current numbers. You can see in the literature numbers that are 20 times greater than this. But certainly, we're talking in the billions of dollars worth of minerals, simply looking at the metals in the asteroids. A meteorite is about 10% metal, and because it's never been in a planet that melted and had all this metal go into the core, the metal includes the full cosmic abundance of things like gold and platinum, which are very rare on planet Earth. You may recall in 2013, there was a day, the 15th of February, when two visitors from space came very close to the Earth. Asteroid 2012 DA14, about 30 meters across, came closer to the Earth than synchronous satellites orbit. The other one came even closer. It exploded in the atmosphere over the city of Chelyabinsk. 1,500 people wound up going to the hospital because of flying glass during the explosion. And this illustrates the size of these bodies. When an astronomer talks of a 1 kilometer body, it's easy to say that that's very small, 1 kilometer. There are thousands of them. There are probably 1,000 that pass close to the Earth as near-Earth asteroids. But 1 kilometer isn't actually a very large size on a human scale. I could easily see a body like 2012 DA14 being attacked by robots, pulled apart, and the minerals recovered from it. The amount of money you're going to get from one of those is not that spectacular, maybe $500,000. And so if it takes several billion to get out there, you're going to have to consume an awful lot of them. But bodies like that come close to the Earth at the rate of about 1 per week. So there are such bodies out there. And there are already many corporations set up, designed to invest. You can invest your money with them, and they are hoping to start mining asteroids in the next 10 years. Now, the fact of the matter is that even NASA is interested. This was a PowerPoint set that I was given by a friend on looking at the engineering of how you go to an asteroid, how you put your spacecraft there, how you pull the pieces out of it, how you turn it into something that you can actually mine. In the short run, the most valued material will probably not be platinum or nickel or gold, but water. Because if you actually want to be in space, either to use the water as a source of rocket fuel or in order to support human life in space, it costs more to lift a kilogram of water off the Earth into space than the value of a kilogram of platinum. And so in the short run, that's where most of the mining is going to take place. But in the long run, in the next 100 years, one has to recognize that mining materials in space is going to be a winning proposition. Already, a number of small nations like Luxembourg, the UAE, the Isle of Man are setting up places where you can incorporate, partly because there are laws like the UN Space Treaty which limit how much you can exploit space materials. The arguments that the lawyers have recently come up with is, if you can move it, it's yours. And that's another reason why people are looking to grab small asteroids, pull them out of a solar orbit into a lunar orbit, and have them parked someplace where you can take them apart at will. If this happens, there are a number of interesting sustainability issues. On the one hand, because you're doing this in space with an awful lot of asteroids, you have, compared to human needs, an essentially unlimited resource of material. Because it's happening in space, you have 24-hour solar energy, so you also have the possibility to not only mine the material, but actually do your manufacturing in space. And that could mean eventually a plentiful supply of low-cost goods, and one that's not tied to any one nation. And certainly moving mining and moving manufacturing off of planet Earth preserves planet Earth. That's all to the good. But there will be disruptions. For one thing, if the resources are not in the hand of one nation, they will be in the hand of a few multinationals, or perhaps we should call them multiplanetals at this point. For another, there are a number of third world nations whose economies depend on exporting raw materials. And that will disrupt their economies. On the other hand, those raw materials are also the sources of many wars, many civil wars, and a lot of discord, especially in, for example, the Great Lakes region of Africa. The other thing to remember is that there's very little opportunity for employing unskilled labor when you're mining asteroids. It's mostly going to be great for clever robot operators and engineers working for a small number of people. It's not an opportunity for employing large numbers of unskilled people. I end by reminding us of what Laudato Si has said on the nature of resources. Exhausting resources on Earth is bad in that it ultimately disrupts human society. But we have the issue of the present disparity of technological investment in a small number of places and people compared to investment in the human family. The need for a type of human employment that matches everyone. And as the Pope reminds us, that a sense of love, a sense of human worth in social life, whether it's politics, economics, or cultural, has to become the highest norm. The bottom line in deciding whether or not to invest can not only be in dollars and cents, but it must be in some sort of measurement of human value. Thank you very much.